Let's continue exploring ICS networking and protocols in this submodule. Upon completion of this lesson, students should be able to describe the various wireless ICS protocols, describe the important factors in choosing a wireless ICS architecture, differentiate ICS network protocols, describe the relevance of deep packet inspection to security, describe the frame structures of various ICS network protocols, and analyze ICS network packet captures. The wireless variety of ICS protocols and standards includes wireless HART, IEEE 802.11 Wi-Fi, Ethernet radio, IEEE 802.16 broadband, ISA 100.11a, and WIA PA. The wireless HART based on the IEEE 802.15.4 technology released in 2008 has the largest install base. The critical factors in designing and implementing an ICS wireless architecture include the following. Scalability. The ICS wireless architecture may start small. However, a provision for future expansion must be in place. Security. It is imperative that security must be one of the primary considerations and not just an afterthought when designing an ICS wireless architecture. Legacy infrastructure. It is important to adapt to the existing communication infrastructure to mitigate a costly transition or conversion. System and capability and capacity. The capability and capacity of control system components to work with the proposed wireless technology must also be considered. For instance, the speed and bandwidth of the wireless protocol may not be appropriate to the operating requirements of the existing control system. Wireless HART is a protocol for communication designed for measurements in industrial process and control applications. It is an independent vendor and an open standard. Due to these two qualities and features, it is the world's most widely supported protocol for the process industry. Currently, thousands of HART-based products are available from various vendors. The protocol is referred to as a hybrid protocol in that it combines both digital and analog communication. The HART protocol can communicate one variable through the use of a 420 milliamps analog signal, while at the same time communicating added information on the superimposed digital signal on the current loop. Wireless HART is designed using a mesh networking technology. In a mesh network, a device can serve as a router for messages from other devices. This capability allows the extended range of the network and enables reliability through the redundant communication routes in a radio environment that are commonly found in process networks. The following comprise a typical wireless HART network. Wireless field devices. These are the process controllers or field equipment. Gateway. This is the communication interface between the field devices and the host applications on the industrial communication network. And the network manager. an application that is responsible for network configuration, traffic management, message route management, and monitoring the network health. Wireless HART is mostly used for sensors and actuators, routing equipment controls, safety application monitoring, and flexible manufacturing in which plant reconfiguration is required by certain specific products. The Application Layer Data Unit, APDU, of the wireless HART is an aggregated collection of commands that is encapsulated by the Transport Layer PDU, TPDU. Each command starts with a 16-bit command number, followed by the size, length, of the command and the payload. The 16-bit command number indicates that there can be as many as 65,535 commands. The APDU structure is depicted in the figure. The Network Layer Protocol Data Unit, NPDU, is shown in the figure. It consists of the following: a 1-byte control field, which specifies an addressing scheme employed and indicates if special routes are used. A 1-byte time to live, TTL field, which indicates the maximum number of hops that the packet is allowed before it is discarded. A 1-byte absolute slot number, ASN, snippet field that provides performance metrics and diagnostic information. It includes the creation timestamp of the packet. A network ID, which specifies a unique network number to which the packet belongs. A graph ID, which is used to route the packet across the network. A destination address and a source address for routing purposes. An additional field which may contain some additional routing information. A security sublayer field consisting of a 1-byte control field, a 1-byte counter, and a 1-byte message integrity code, MIC. The control field specifies the type of security employed. The security type and the counter field are used by the application security algorithm. The MIC field is used to check the data integrity. And an encrypted transport layer PDU, which encapsulates the APDU. The Institute of Electrical and Electronics Engineers, IEEE, created the 802.11, a wireless local network, WLAN standard with 2 megabits maximum bandwidth in 1997. In 1999, the need for more bandwidth ushered in 2 expanded WLAN standards, 802.11b and 802.11a. The 802.11b standard, working the 2.4 gigahertz industrial, scientific, and medical ISM band, was able to deliver a maximum bandwidth of 11 megabits per second. The 802.11a, operating on the higher frequency 5 gigahertz ISM band, was able to deliver a maximum bandwidth of 54 megabits per second. In 2002, the 802.11g emerged. It combines the technical merits of 802.11a and 802.11b to to deliver better performance. In 2009, IEEE ratified the adoption of a new WLAN standard 802.11n. This standard utilizes a new technology called Multiple Input, Multiple Output, MIMO, which utilizes multiple antennas to enable simultaneous multiple I/O operations. The standard is rated at a maximum throughput of 300 megabits per second. The newest standard, 802.11ac, utilizes the dual band technology, i.e. simultaneous transmitting on both ISEM standards, 2.4 gigahertz and 5 gigahertz channels. This standard is designed to deliver maximum bandwidths of up to 450 megabits on the 2.4 gigahertz channel and 1300 megabits on the 5 gigahertz channel. The IEEE 802.11 frame structure is shown in the figure below. The duration ID field is used for all the control type frames, except with the subtype of power save PS pole to indicate the remaining duration needed to receive the next frame transmission. When the subtype is PS pole, the field contains the association identity, AID, of the transmitting station. The address fields represent MAC addresses of the source, the destination, the AP, and the ad hoc station. The sequence control field contains a 12-bit sequence number subfield and a 4-bit fragment number subfield. The frame body field contains the data or information included in either management type or data type frames. The frame check sequence FCS field contains the error checking information. A cyclical redundancy check, CRC, is used over all the fields of the MAC header and the frame body field to generate the FCS value. The IEEE 802.11 Medium Access Control, MAC, frame structure is shown in the figure below and consists of a MAC header, the frame body, and a frame check sequence, FCS. The number of bytes for each field is also depicted. The frame control field, shown in the lower figure, contains control information used for defining the type of 802.11 MAC frame and providing information necessary for the following fields to understand how to process the MAC frame. The subfields of the frame control are the following. Protocol version. This represents the version of 802.11 protocol used. Type and subtype. These fields determine the function of the frame. There are 3 frame types: control, data, and management. Each of these types has multiple subtypes which determine the specific function to perform for its associated frame type. To DS and from DS. These fields determine whether the frame is going to or exiting from the distributed system, DS. More fragments. This field indicates whether more fragments of the frame are to follow. Retry indicates frame retransmission. Power management. This field indicates whether the sending station is in active or power save mode. More data This field indicates to a station in power save mode that the access point AP has more frames to send. It is also used for APs to indicate that additional broadcast or multicast frames are to follow. WEP. This is the wired equivalent privacy WEP flag. It indicates whether or not encryption and authentication are used in the frame. It can be set for all data frames and management frames, which have the subtype set to authenticate. Order. This field indicates that all received data frames must be processed in order. High-speed frequency hopping Ethernet data radio communications on the license-free 900 MHz and 2.4 GHz bands have also been deployed for telemetry and SCADA applications in the water, wastewater, gas, oil, and mining industries. Most of these Ethernet radios provide a point-to-point or point-to-multipoint setup and can transmit at a speed of 512 kilobits per second at a distance of at most 45 miles. The J-Series Trio radio, manufactured by Schneider Electric, employs several layers of security. The first layer uses the network name for deriving the hopping sequence. The second layer of protection uses the serial numbers as trusted labels. The third layer is through the use of a 256-bit AES encryption key to encrypt the data that is to be transmitted. Modern cellular networks are currently being adopted at an unprecedented pace by utility companies to provide the communication functions needed to manage vital control systems. Cellular system providers now offer data services over the 3G networks such as Wideband Code Division Multiple Access, WCDMA, and high-speed downlink packet access, HSDPA. With the introduction of 4G technologies to work with the newer mobile devices, long-term evolution, LTE, technologies are projected to have an impact on the remote management of control systems as well. Although these publicly accessible cellular modems are provided with built-in security features such as IPsec complement virtual private network, VPN, and firewall capabilities, vulnerabilities still exist. The ISA 100.11a standard is similar to the wireless HART and the WIA-PA in that they all rely on the underlying physical layer of the IEEE 802.15.4 protocol. They all provide a data rate of 250 kilobits per second on 15 globally allowed channels on the ISM band. The ISA 100.11a data link layer provides support for the creation, maintenance, and packet forwarding. It uses graph routing for packet transmission. Graph routing provides for a number of different data paths for different types of network traffic within the data link subnet. Devices use multiple graph routes to transmit different types of data, which may vary from small chunks of data for equipment monitoring to large data blocks for process control. Depending on the type of data and process requirement, the system manager creates and assigns the appropriate graph route. The design criteria for ISA 100.11a include the following: flexibility, support for multiple protocols, use of open standards, support for multiple applications, reliability, including error detection and channel hopping, determinism, TDMA, QoS support, and security. The ISA 100.11a standard uses the IPv6 addressing schema for end-to-end routing on the network layer. On the transport layer, it supports a connectionless service based on UDP with an enhanced message integrity check and end-to-end security. A quick glance on the basic reference model of the ISA 100.11a standard mapped with the OSI standard model is shown in the table. When the ISA 100.11a standard utilizes the Internet Protocol IP addressing scheme, the wireless HART and the WIA PA standard uses proprietary addressing schemes. The WIA PA standard is proposed by the Chinese International Wireless Alliance, CIWA, in 2007 and was approved as a publicly available specification by the International Electrotechnical Commission, IEC, and renamed as IEC 62601 in 2011. The WIA PA standard defines 5 types of devices: a host that acts as the main interface to process operators, a gateway that provides the connectivity between the control network and the wireless network, a router that is responsible for the efficient and effective routing of network packets, a field device that acts as the main process enabler, and a handheld device, the portable wireless instrument. The WIA PA standard allows either a mesh or star network topology. Before joining the network, a device has a 64-bit physical address. After joining the network, it assumes a 2-byte address representing a 2-part addressing scheme, an 8-bit cluster address, and an 8-bit intra-cluster address. A typical network layer packet frame is depicted on the figure. Similar to other wireless standards, the WIA PA does not have the full implementation of the OSI standard model. A glance on the basic reference model of the WIA PA standard mapped with the OSI standard model is shown in the figure. Deep packet inspection is the process of allowing packet inspection devices, such as firewalls and intrusion prevention systems, IPS, to perform an in-depth analysis of packet contents. This in-depth analysis is much broader than common technologies in that it combines protocol anomaly detection and signature scanning to realize its potential. For more comprehensive literature reviews on various tools and techniques for the development of DPI systems, the astute reader is referred to the work of Antonella et al. ICS packet capture and analysis can be accomplished using freely available tools such as WinDump and Wireshark. These network packet analyzer tools provide a mechanism to drill down into each packet. These are very convenient tools to use, especially with ICS packets, since the control information is most likely encapsulated by the traditional protocol frames such as TCP and UDP. To be able to perform an effective ICS network traffic analysis, a solid understanding of the various ICS frame structures is required. The following sections provide high-level descriptions on the analysis of sample captured ICS packets. Now let us revisit the generic Modbus frame, which is depicted in the figure. The single octet address field identifies the controller or device to which the request response is being directed. The single octet function code can be any code from one of these three categories: public, user-defined, or reserve function codes. The data field contains the information that is being requested, the exception code, or the information, such as the addresses and number of registers which are being passed to the server. The error check field contains the longitudinal redundancy check, LRC, information for the ASCII mode and for the RTU mode, the cyclical redundancy check, CRC, information. The Modbus organization, modbus.org, extended the Modbus protocol to work over the Transmission Control Protocol, TCP, by encapsulating the Modbus PDU with the Modbus TCP ADU. The protocol is registered to utilize port 502 and is realized by augmenting the standardized Modbus PDU with the Modbus Application Protocol, MBAP header, as shown in the figure below. The MBAP header is made up of the following: a 2-octet transaction identifier, TID, a 2-octet protocol identifier, PID, a 2-octet total length, LIN, in bytes of the remaining fields, and an octet indicating the unit identifier, UID, which identifies the remote slave connected by a serial line. IEC 60870.5 is an open standard that is used for transmission of SCADA telemetry data and control. The figure below depicts the ACPI and ASDU components of the packet structure. The figure below provides the details of transmission, such as control type, code, transmit and receive sequence numbers, and reference descriptions. A careful scrutiny of the information provided would reveal the following information: ASDU type code 50 with reference C_SE_NC_1, set point command short floating point number. The APCI is information type with transmission sequence number 74 and receive sequence number 16. The cause of transmission, COT, is 3, spontaneous. The information object address, IOA, of 12, and a floating point value of 9.87. A deep packet inspection of an Ethernet IP packet can be done skillfully by referring to the detailed descriptions of each of the encapsulation header and data fields in the previous section. As shown in the figure below, The source port set to the value 44818 indicates Ethernet IP running over the Transmission Control Protocol, TCP. Further, the sender context and option fields set to 0 indicates a normal transmission. As previously discussed, Ethernet for Control Automation Technology, EtherCAT, is a control system protocol that is mainly used to satisfy very high performance requirements in the manufacturing environment. The EtherCAT process object, PDO, known as telegram, consists of one or more datagrams, each serving a particular memory area of the logical process images of up to 4 gigabytes in size. The EtherCAT telegram header consists of a length field, a reserve field, and a type field, which indicates the nature of the data carried by the EtherCAT telegram. ICS communication messages are transmitted and encapsulated on EtherCAT as a UDP payload using port 0x88A4 34990. EtherCAT is highly susceptible to denial of service, DOS, and spoofing attacks due to lack of authentication. A snapshot of the details of a captured EtherCAT packet are shown in the figure below. Points of interest on this EtherCAT packet snapshot are the following: the Ethernet frame type, EtherCAT 0x88A4, the broadcast write command, BWR, with data value 1100 as the first datagram command, the broadcast read, BRD, writing to slave address 0x0130, and the auto increment physical read, APRD datagram command.